if all polyethylene is made from the one monomer ethylene, why is it that they are found in so many different forms, so many different properties? We've got that lovely bubble wrap that is so much fun to play with from packing materials. We've got detergent bottles, which are very rigid and hard. And then we've got somebody kind of in between, the lovely milk plastic jug. How do they differ on the molecular scale? One of the analogies that's very popular is strands of spaghetti. If you look at the picture on the right, the alginate polymer scaffolding, spaghetti comes to mind quite quickly. I'd like you to appreciate that the way that they can change these polyethylene properties in the bulk is by varying the length of the strands. As you get longer, melting and, well, boiling point is kind of silly, but the melting point increases quickly. The degree of entanglement of the individual strands can vary. And then the density of the strands, the close packing, how much of alignment. And I got to tell you, the more aligned they are, the more crystalline the overall material seems. And that gives it great rigidity and strength. All right, so why would these strands be attracted and hold to each other? Think of them as individual molecules, even though these are inordinately long strands, and think of them as neighbors, just like we talked about with water molecules attracted to each other. It's going to be an electrostatic attraction, or it's going to be an attraction between a positive region and a negative region. And we talked about this with water. We talked about intramolecular being inside the molecule. That's the covalent ionic bonding. And then we talked about the attraction between neighbors is intermolecular, like intercollegiate attraction. This is much weaker, but it's still very significant. There are 4 of these types, and we have, like I say, looked at hydrogen bonding. Let's look at one called dispersion forces. You'll also see this as London dispersion force. And if I abbreviate it as IFAs, these are between the neighbors, we can kind of understand those. But polyethylene, she's not nonpolar. She's all carbon and hydrogen atoms. And we said the individual bonds are so low that we consider hydrocarbons nonpolar. So how do we get them attracted to one another? Here's the hydrogen bonding. This is what we talked about with water. It is a positive hydrogen atom on a neighbor attracted to a negative pair of electrons on another neighbor. And the broken lines are supposed to indicate the hydrogen bonding, and that they're much farther apart than anything inside the molecule. Okay, now dispersion forces. Everything's going to have dispersion force attraction between particles, unless he has no electrons, because it arises from the movement of electrons. So if we look at the helium down here, I've got 2 helium atoms right here. Okay, 1 and 2. All right. And, well, that was interesting. Okay. P. All right. So helium atom 1, helium atom 2. The electrons are moving inside of the electron cloud, and at some point statistically they're going to be on one side of the cloud. Okay? And that's what the next picture is over here. When this happens, I've got my 2 electrons over here, I'm going to end up with a delta negative region. And likewise, they're going to have to bounce always. I'm going to have a delta positive where my 2 protons remain. This is like a domino effect. Now here's helium 2. Here's the other helium atom. And what happens here? Well, it attracts the the electrons to one side, and again I end up with a partial negative end and a partial positive end. And we keep going and affecting all species around us. So these dispersion forces exist between all molecules and atoms. In fact, for nonpolar, they're the only intermolecular force of attraction. Helium has very low forces, very small forces, few electrons. You have to take out a lot of thermal energy to get this stuff to condense from a gas to a liquid, down to 4 degrees Kelvin. It's but for when you have large macromolecules like polymers, they're very, very strong. And you can think of them as Velcro strips, you know, the loop and the hook. And they get very, very tightly held. We kind of see this with necking of a plastic bag. If you take out a saran wrap and you start pulling at it, you'll notice it takes a huge amount of energy to initiate the stretch. That's our Velcro strips. That's our dispersion forces. But as you pull them apart, these are broken. They are removed from one another. And they don't retract like rubber bands. It stays stretched out. Okay, on another note, when we look at polyethylene, and the first polyethylene, and that IFA should be this should be IFA. So I'm going to use abbreviations. I should be consistent. All right. Branching alters the physical properties of polyethylene. The first polyethylene was branched, and that's called low density polyethylene. They can't get, the different strands cannot get close to one another because of all this branching. And we see it used today a lot in plastic bags that you pick up at the grocery store. It's soft, it's stretchy, it's not too strong. Well, about 20 years later, two men won a Nobel Prize. They came up with a catalyst that later won them a Nobel Prize to eliminate or reduce or control this branching, and ended up with straight chain. And we know that today as high density polyethylene. High density, this is the big thing. It is more crystalline. It is less amorphous. You get greater rigidity, strength, higher melting point. You see this in containers, water bottles, even something as hard as lumber and furniture. If you have these straight chains, you get more density, more close packing, and your amount of dispersion forces goes much, much higher. Well, another way you can change the properties is something, we're not going to spend much time on this, but it is an interesting property. You can align the monomers differently. It doesn't make sense for ethylene because that is symmetric. You know, you've got a carbon double bonded to a carbon with some hydrogens. But if you look at vinyl chloride, where you've taken one of the hydrogens and that chlorine, you do have a left and a right, if you will, for these, or a head and a tail. And you can polymerize them in 3 different ways: head to head, tail to tail, or head to tail, or just random. And it does, this microstructure does give them different properties. I'm not going to worry about this, but just want to let you know. So here are the big 6. I want you to be familiar with these. That means I want you to be able to recognize them on a list. There are 60,000 synthetic polymers, so 6 we can handle. They account for 75% of those used in the U.S. and most of what you'll come in contact with. And what do I want to point out? The monomer. The monomer. Hello, ethylene. There's ethylene again for my low density polyethylene. There's ethylene again for my high density polyethylene. They've got properties and uses. Very nice. And vinyl chloride. Hello, this is PVC. Still, in my mind, very much like ethylene, except now I've added 1 chlorine atom, taken away the hydrogen, add that, and changed the properties tremendously. These little circulars are the recycling codes. we are going to talk about those in a little bit. The last 6. Okay. Up here, she makes polystyrene. Oh, and you've heard of polystyrene. There are 2 different forms of polystyrene. You've got the crystalline food wrap, and then expandable. That's your foam cups. But CD cases are the crystalline form. This is ethylene, except I've taken one away and added a benzene. This is a circular, or I'm sorry, a ring of carbon. And the reason why this little circle's in the middle is to indicate that I've got alternating double bonds here. And some hydrogens coming out too. But do not worry too much about that. It is just ethylene with one functional group changed. Again, ethylene, the hydrogen taken away, and a functional group added. She's called a methyl group. Notice it's methane with the hydrogen taken away, and the bond is now to carbon. Propylene is the name of the monomer. Polypropylene is the name of the polymer. And she is dense and hard, opaque and tough. The last one is a copolymer made of ethylene glycol. This is the stuff in your batteries. I'm sorry, in your water radiators, in order to expand the temperature range with which the water stays liquid. You know, it doesn't boil over and it doesn't freeze. And the other monomer is terephthalate. You don't pronounce the pH there. She's quite a different model, but together they make something very common. Polyethylene terephthalate, which we, thank you very much, call PET or PET. And look at the recycling number. Number 1, and this is very much so top of the recycling. The percentage of material recycled is PET. It is in your soft drink bottles, your clear plastic food containers, beverage fabrics, all over the place. It is shatter resistant, strong, and it is most costly, but it is used a lot. The monomers make the polymer, right? Okay, but now I've taken ethylene and I've started adding different side groups we call now functional groups. This is a big concept in chemistry, so I want us to spend a little bit of time on this. Functional groups are a distinctive arrangement of atoms bonded, not individual atoms just plunked onto a frame, but we have seen them before. How about that? This guy's called hydroxyl, and he forms our alcohols. So if I had methanol, I would take one of the hydrogens away and add an OH group, and there she is. Another one I want you to know, the carboxyl, not know, but you know what I mean. I want you to be able to recognize it, be familiar with it, pick it out in a lineup. She's got this alcohol here, but because of this carbon oxygen double bond, this has a partially positive area here and can come off as an H+. So she is an acid. In fact, most natural acids are carboxylic acids, acetic acid, malic acid, like in milk, they are these carboxylics. Ester, ester, I don't know, you probably heard of esters. They're very sweet smelling. Here you've taken off the hydrogen and added a carbon from the carboxylic acid. Amine, I want you to know the amine. The amine, we're going to see when we look at amino acids. Hey. It is got a nitrogen in him, and he is a derivative of the ammonia. That's where he's easy to remember. All you got to remember is nitrogen. But amines act very particular. They have their great physical and chemical properties. The other one's the amide. Again, we're taking off one piece and adding that. And then phenyl. A phenyl group, we've talked a bit about. She's got 6 carbons. And here, she's got an alternating double bond. And then a hydrogen coming off of each one of these to give each carbon 6 bonds. I'm sorry, 6 bonds, good. 3 bonds. But functional groups, that is an important idea, because you add a functional group to a chemical, you change her properties, PDQ.